All right, welcome to this webinar on maximizing our impact, a call for the standardization of techno-economic analyses for sustainable energy systems design research. Our speaker today is Professor Thomas A. Adams. He is an associate professor in chemical engineering at McMaster University. His research interests are in process systems engineering, particularly with regards to modeling, simulation, and design of sustainable chemical and energy processes. So with that, I'll go ahead and turn it over to Professor Adams.
Well, thanks a lot, John. Thanks everyone for being on the call. Excuse me. I'm going to talk today about something that's been really exciting to me over the past couple years. It's been basically 10 years in the making, involving an existential crisis and the general changing of everything that I thought I knew within chemical engineering and energy systems. And basically where it's come to is a realization that in order for us as a community to have a greater impact as energy systems engineers, we really need to focus more on speaking the same language in order to address major world problems with regards to climate change and other environmental factors. So today I'm going to talk about how I think by standardizing the way in which we do business, in some cases, we can really make real change together as a community. So that's the overarching goal of the talk. So if you are interested, this will be posted later, of course, but the slides are also available on LAPS. That's the Living Archive for Process Systems Engineering. So this is the sort of pre-print, post-print, and model repository for process systems engineering, partially funded by ASCHE and CSHE and another number of other groups. So you can download the slides here. At the bottom of every slide, there'll be the link. So the project website is at psecommunity.org/standards. In addition, there's also links to the research that led into this and other kinds of materials around the project. So you'll have that available to you. And just to put everything into context with what I'm going to talk about today, today I'm representing the Canadian Society for Chemical Engineering, so the CSCIG. I'm the chair of the Systems and Control Division there. I've also been very active in AICIG. I'm coming up to be one of the new CAS directors with the next term. And so I've been sort of integrating around North America around the development of a new ISO standard relating to eco-techno-economic analyses. Okay, so I'm going to talk today about why we need a standard, what it might look like, the kind of value we can get out of it, and how you can get involved today. And this is well within our wheelhouse at CSCIG. We actually just recently completed a national standard of Canada by one of our other divisions, and so we're following the same kind of model that we used in that case, in this case. And this is yet another stop on my lecture tour. So I've been traveling around North America, giving essentially the same talk in different forms depending on the audience. And so today is my virtual stop with CAS 10. I know we have someone here from Eastman. I actually did a talk with Eastman not too long ago, so I'm glad that word has reached you to come back and get some more. I'm doing another talk at MIT coming up, and then probably a few more along the way. So placing everything in context. Okay, so the main motivation within my research program, what I really am is a process systems engineer. And I look at all the ways of combining things like coal, natural gas, biomass, nuclear energy, wind, solar, together and converting them to energy products. So that would be synthetic fuels, alternative fuels, biofuels, electricity, olefins, ethers, esters, that kind of thing, and doing everything within a sustainability context. So from my own perspective, everything that we need to do has to meet the triple bottom line of sustainability. It means every idea for it to actually change the world in a positive way, and has to be economically sustainable. So it has to have a business case, has to be environmentally sustainable. So it has to have a sort of a provable positive impact on the environment, or at least not as bad as we used to do. And it has to be socially sustainable, which means you have to be able to get the support of the community and government and policy on board. And so there was one study that we were asked to do around looking at comparing different kinds of power plants that have carbon capture and sequestration in them. And I spent a great deal of my career up to this point studying and researching and designing aspects of these whole systems or parts. And after 10 years, I couldn't tell you which kind of power plant we should really be building in terms of how are we going to try to mitigate climate change with CO2 capture and CO2 avoidance. And so what I want to do is I just want to show you the general premise. There's really three different kinds of power plants in terms of how you would avoid CO2 emissions. So the first one is a post-combustion strategy. Okay, and this is the idea where you have a classic combustion-based power plant. Maybe it's coal, maybe it's gas, and basically you can generate power through combustion turbines and or steam cycles. But fundamentally, after you've produced power, you have your exhaust, which is CO2 and nitrogen. Okay, mostly nitrogen, but all of your CO2 in very large volume is here. And normally, we would just vent this to the atmosphere after cleaning. But a post-combustion strategy uses a solvent-based or other kind of system that would remove CO2 from that nitrogen, okay, and then that would then be sequestered. And there's lots of different ways you can do this. In Canada, we have a power plant in Boundary Dam in southern Saskatchewan, where they have a solvent and they capture a very large amount of CO2. It's the biggest working CO2 capture system in the world right now, and that's what we have to start with. So that's sort of our basis. But there's a lot of other approaches we can try, different solvents, membranes, that kind of thing. Pre-combustion strategies say, okay, the CO2 nitrogen separation is a very difficult problem. And so let's completely rethink the power plant design just to make it easier to capture CO2. Okay, and there's a lot of different ways you can do this. But what you can do is you basically convert coal and gas and that kind of thing into synthesis gas or syngas. All right, that's a mixture of CO2 and hydrogen. All right, and the idea is that all of your carbon by this point is in CO2 form, and all of your hydrogen is in H2 form, and most of your energy that you started with in the fuel ends up in that H2. Okay, and there's lots of different ways you can do this. Primarily, usually you need a very high purity oxygen stream in one way or another. And there's lots of different technologies depending on the fuel, but ultimately you end up with the CO2 hydrogen separation problem. Okay, and you can do the same kind of approaches as the post-combustion. You can use solvents, you can use membranes, but CO2 hydrogen is a much energetically easier separation than CO2 nitrogen. Okay, and so that's the premise, is that this step is so much easier. You know, hopefully it's worth it to do all this extra work up front. Then you end up with this hydrogen, and you can use that for power generation and a number of things. It can be combustion turbines or boilers or whatever, or fuel cells and other uses as well. So that's the idea, is your fuel ends up happening devoid of carbon. Okay, and then there's a third approach. And that third approach is a little more advanced even than that, although this is really not commercialized either quite. It's that you want to separate oxygen from the air. Okay, so CO2 hydrogen still is quite energy intensive. So the question is, okay, let's separate oxygen from the air, and in some way, okay, oxygen will somehow make it and oxidize our fuel, okay, in an arrangement where there's no nitrogen present. So we get nitrogen out of there way up front. All the oxidation happens without nitrogen around. And then what happens then is your exhaust is just CO2 and water. Okay, so ideally all the carbon ends up as CO2, all the hydrogen ends up as water. And then you have a CO2 water separation, which ultimately is quite easy. Energetically, it's just condensation of water, which is orders of magnitude in some cases easier than this. So the question is it worth everything upstream to make this downstream part easy? Okay, so just to summarize the sort of different kinds of options. So with post-combustion, we have solvent-based post-combustion. That tends to be at atmospheric pressure. Membrane-based post-combustion actually tends to capture, so you can use a membrane to separate CO2 and nitrogen. That actually tends to be more vacuum because it's pressure differential driven. So you need high pressures up front and low pressures on the back to drive that CO2 across the membrane. Solid-based post-combustion. This is the idea that you actually react the CO2 into some solid form, separate the solid from the nitrogen, and then react it back to CO2 again. Okay, this is also an atmospheric pressure type system. Okay, solvent-based pre-combustion. These are things like okay, using solvents like IGCC or preforming natural gas. So these solvent technologies have been around for a very long time. It's just that now we want to use them in very large measure for CO2 purposes. And the nice thing here is this can happen at high pressure, which means the captured CO2 is at a higher pressure for sequestration. And you can also use membranes. The CO2 hydrogen membrane can be more effective than CO2 nitrogen in many cases. These more advanced ones, oxyfuels, you may have heard of. This is the idea where you make high purity oxygen and you combust your fuel in that instead of air. Chemical looping, this is an interesting idea where you use a metal carrier and you react your fuel with a metal oxide like iron oxide or nickel oxide. Okay, and so oxygen is removed from the nitrogen via this metal, and then you recycle this metal back to the air reactor, that sort of thing. So the idea is that this is a very different idea with solid carriers, and then we have solid oxide fuel cells, and these use basically electrolytic, electrochemical processes where you have oxygen nitrogen separation happening at the same time as your fuel oxidation. So oxygen moves from the cathode into an anode, and then that's where the fuel is oxidized. So nitrogen never gets into your fuel. Okay, and all of these have a CO2 water separation downstream. Okay, and I don't want to go into all those details. I have other presentations and materials. If you want, just contact me. But the basic premise is I spent 10 years looking at all of those things. Okay, and after 10 years, I could not tell you which one I could recommend. All right, and that's a real problem, right? And I have my whole career based around understanding these processes and trying to figure out what we're going to do. Okay, so somebody had encouraged us for a particular journal article, that was the motivation, but to look at these processes and just come up with an idea. What do you recommend? Okay, that turned out to be really, really difficult. Okay, so what we tried to do was a meta study. Okay, and a meta study is when, like in medicine, we do this all the time. In medicine, it's when you look at a bunch of studies and then you try to make one conclusion based on all of those. It's not like a review necessarily where you're talking about what's been done. It's more like you're piecing all together the pieces of the puzzle and you want to make a final conclusion. And so we tried to do that with this. We looked at over 100 different papers on all of these topics, okay, me and my team. And one of the key problems, though, is when you looked at each individual paper, there was no way to do a systematic comparison between a process. Okay, so if I look at one paper and they say, oh, okay, it's got this efficiency, this cost of electricity, this amount of CO2 emissions, whatever, and I look at a different paper, all right, it is completely impossible for me to look at those same metrics in another paper and compare them. You can't accept them at face value. There's no consistency between these studies in terms of all the fundamental assumptions. They're all different locations of interest, different P performance indicator definitions, different product years, different analysis boundaries. Okay, totally different. All right, and what ends up happening is every single person claims that their own process that they're studying is the best compared against something else. Okay, and it's ridiculous. Okay, there's no way every single one of these can be the best. But all you have to do is you have to find something else that's not as good as you to compare it against, and then you look good by comparison. And this is really a product of our culture in research, that we don't like the negative result, it's called. It's very difficult for us, we think, to publish ideas that don't look good. Okay, so culturally, this is a natural outcome of just the way science works within our field. Okay, but the end product is I can't look at the literature and just have a meaningful result by looking at all these 10 different categories with 100 papers. Okay, so here's a great example. Okay, one metric I'm going to show you today is the cost of CO2 avoided, CCA. Okay, and basically you have a numerator and a denominator. The numerator is the extra cost you pay to do something green. Okay, so let's say you normally have a bottle of water and you want to buy a box of water because that's more environmentally friendly. Boxes of water are very trendy right now. So you're going to pay, let's say, an extra $1 for that same amount of water just to be green. Okay, and then your denominator is the amount of emissions that you avoid in terms of CO2. So this is global warming potential, okay, that you avoid by doing that. Okay, that's the denominator. And you get a number like dollars per ton. All right, and a really good number to target is about $50 per ton of CO2 avoided. That's the kind of numbers we're talking about. It's a good order of magnitude. Okay, but within the literature, there's such a huge disparity between what the base cases are, what these metrics are, global warming potential and LCOE, that you end up with just a bunch of noise. Okay, so for example, on the right, okay, all I've done is I've taken, we found 44 examples within the supercritical pulverized coal with carbon capture. So that's the sort of the state of the art. Then there's integrated gasification combined cycle, and then oxyfuels, all from coal. Okay, and these are averages of the as reported cost of CO2 avoided. Okay, with some error bars here. All right, and basically what it says is if I just took the numbers at face value in the literature, they are all statistically equal. Okay, essentially. And so, of course, I can't tell you which one's the best because if with that information, they're all statistically the same. So what's the point? Okay, why are we doing all this research if they all come out exactly the same? Okay, and that's a product of the noise. So what we ended up having to do, okay, after we looked at all this data, got no information, we said, okay, we need to standardize the way in which we do our analysis. All right, so we took all of that information and we basically redid all the calculations under a consistent set of conditions. All right, so we have a consistent size, 550 megawatt net AC plant gate, high quality, high voltage power, okay, at the plant gate. Okay, we have a way of converting costs if someone has a study that was done at a different size to give us an estimate of what the same cost would be at this particular size. Okay, we can standardize for time and place, in our case, first quarter 2016 in North America. And we can do that with different kind of plant cost indices with Europe and North America and different places around the world. We can convert them in time, and we can convert them in place using purchasing power index. Okay, so if a study was done in 2014 in Germany, I can get a really good estimate for what that same plant would look like at 2016 in the United States. Okay, same fuel. Okay, so normalizing the fuel, and I say not just the cost of that fuel and its content, but its entire supply chain. Okay, so for example, with conventional natural gas, not only can I use a standard cost, but I can use the entire supply chain, the exact mix of shale gas, conventional gas, imported gas, LNG, right, and how coal bed methane, and how all of that affects globally the emissions of that supply chain on the U.S. pipeline, and so that we can normalize. Standardizing how much CO2 is captured. So one of the big problems is with a lot of these studies, they'll say, okay, I capture all the CO2, but they captured it 1 bar. Okay, that's not useful. I need to get it up to pipeline purity. So we have standardized the pressures and the purity and the capture rates. Okay, making sure that everything has like to like. Standardizing the life cycle analysis. Most of these studies ignore things like NOx. Okay, so accounting for NOx uniformly. Standardizing the boundaries and the supply chains around our cradle to plant life cycle. Okay, and that's very important. Okay, this is one of the most important things for the cost of CO2 avoided, and this is the whole point of what we're doing. Okay, and then we have the same standards for CCA. All right, so once we can do that, we sort of go in the underbelly of each paper, we can extract the data we need and convert everything. Okay, we can get some really useful information out of it. So before we had the same blue chart on the left, on the right now we have what happens to these numbers if we just recompute the exact same information in a standardized form. So now at the same time and place, each individual process is statistically significantly different from the rest. And if you look at this, IGCC looks really, really bad compared to supercritical pulverized coal. All right, and that makes sense now, but there were 2 cases in the United States where 2 of these plants were attempted, and both of them, after more than $10 billion in construction, were switched directly to natural gas. Okay, and so like with that kind of economic outcome predicted here, why did we do that? Why did we waste $20 billion on these 2 examples? Okay, and then down here we have oxyfuels, and now all of a sudden oxyfuels are looking really, really good, okay, compared to the state of the art. So maybe we should be starting to think in this category. All right, and that just gives you some raw averages. What we can do with this crazy looking plot, I'll spend a minute on here, is we get a lot more interesting picture of what's going on. Okay, what we've got is on the y-axis, okay, on the left side, we've got the cradle to gate exit greenhouse gas emissions. So this is basically per electricity delivered, the life cycle, okay, includes the drilling, the pipelining, fugitive emissions, construction of the plant, CO2 capture, CO2 sequestration, construction of those pipelines, everything except the transmission and use of the final electricity, okay, so that's where we draw the boundary. And these are all done standardized. On the bottom, we have the levelized cost of electricity under those same standard conditions. All right, and each different sort of point is within a category. So we have purple X's, and I hope you can see my mouse. I'm not sure if you can, but purple X's are top center, okay? And there's a nice oval here, and everything in that oval is supercritical pulverized coal with carbon capture. This is what we have in Canada. This is the thing to beat, okay? And what's really nice is we've reduced all the macro noise because of non-standard way of thinking and a non-standard way of doing the analysis into now just micro noise. All right, so the differences in these studies, and this is everything we can find in the literature that has a techno-economic analysis that we have enough information to use, it fits into this nice range between 250 to 350 in greenhouse gas emissions, 80 and $140 per megawatt hour. Okay, a nice oval. And that's nice because that means that the community to collectively and independently have sort of agreed on this range under these standard conditions. And you're looking at macro noise. People have different estimates for cost. People have different solvents, different situations they're doing it. Okay, that's fine. Different turbines, that kind of thing. But that's macro noise. All right, and then we have green diamonds. Okay, that would be the same plant but with membranes instead of a solvent-based capture. Okay, for post-combustion. All right, there's the green diamonds, and they sort of overlap, and they go a little bit better because you want to go down to the left. Okay, but these points that are outside of the supercritical pulverized coal with solvents, those are for fictional membranes that have never been designed. Basically, they're fictional hypothetical membranes. So that's sort of the best that technology can ever go. Okay, and you say, well, wait a minute, should we really be investing tons of money in pre-commercial membranes when our existing commercial solvents work essentially equal? Is it worth going that little extra distance? Okay, I'm going to skip some of the other ones. We have this red circle here with the red squares. All right, that is oxy-fuel combustion. All right, so the community has sort of centered in this region, and it is completely outside the oval for the purple X's, the supercritical pulverized coal. So oxy-fuels, the community has agreed, is significantly lower greenhouse gas emissions at even lower cost. Okay, but this is pre-commercial. We don't have this at commercial scales. So this tells us this is where we need to go. All right, we have gray circles a little bit lower. That's also contained within oxy-fuels. This is chemical looping combustion. Also looks very good. There are fewer studies that has more to, that's why the circle's smaller, probably. Okay, but it still looks very good. But then we have blue circles to the left of it. That's natural gas with combined cycle. Natural gas combined cycle with carbon capture and sequestration. We can do that. We have that technology. All right, and it just beats the pants off of all the other coal options we talked about. Okay, so now we're saying, well, wait a minute. Why should we use coal at all? Why did I spend 10 years of my research career looking at coal-based systems? All right, and that was my big existential crisis when I see this. All right, if it's so much cheaper and so much lower impact, why are we doing any of this stuff? Okay, so those are some really interesting big picture things we can see. And below that, we have these triangles. So open triangles are coal-based solid oxide fuel cells, and closed triangles, the black ones, are gas-based solid oxide fuel cells. Okay, and these are significantly better than everything else. All right, but they are at the 250 kilowatt scale right now. Okay, so they're the farthest away from commercialization. So what this means is we have a huge, there's a hope for coal in the fuel cells and pretty much nowhere else, at least in North America. All right, and gas with fuel cells become clearly the winner. So that tells us a pathway. We're up in the purple X's. We need to get down to the triangles, and this is the technological route by which we can achieve that. Okay, but because we've eliminated the macro noise by doing the standards, we can see these results. Okay, so from a big picture, what I learned from this is that it was so hard to do this study because we can't take anything at face value. But the rewards of doing those meta studies are very, very significant. Okay, because now I can finally recommend with a clear and consistent message, these are the technologies we need to invest in. This is where the money's got to go. This is the direction we need to head, okay? And we can sort of weed out the wheat from the chaff, all right? So this is when I started thinking about standardization. It would be a lot easier if we just all did this, okay? And that's really where I got on the quest to bring this forward. So the proposal that I'm putting forward now is based on this sort of this main message, okay? Is what I want to do is I want to have a way where we do these analyses, where we have a standard base case for comparison. Okay, and there's a lot of these things out there. People might publish a baseline. The NETL does this quite a bit. We have someone from there on the call right now. But looking at choosing where we all agree one process to sort of beat up on together. All right, it doesn't have to be the best. It could just be something we all agree to compare it to. All right. We need consistent life cycle analysis methodologies. There is an ISO standard for life cycle analysis, but it is far too vague. It gives too much freedom for boundary definitions, assumptions, methodologies. I need something more specific that we'd all agree to for this purpose. Standard sizes. I'll talk about why that's so important. Standard definitions, domestic. Standard cost estimation methodologies. That one's going to be harder for us to agree on. We may not be able to include it. Transparency is very important to me. Data formatting. Okay, and this is why I'm working with Standards Council of Canada now to hopefully produce an ISO standard that we'll all agree on. So this is my key vision, all right? And there's different stakeholders, there's different reasons why people will use and produce material with the standard and then use that same material. Okay, so if you're a researcher, if you're an author, all right, basically this is what I expect you to use. All right, what I envision is you would do your study, your eco-techno-economic analysis, just as you normally would. The difference is you would consult our standards table to choose the kinds of assumptions that you would normally do in your analysis. So things like, okay, let's say I'm doing a fuels in a North America at a large scale application. Okay, I would go look up the standard. Let's say it's PSE3, made that number up. All right, I would look and I'd say, okay, this is the debt to equity ratio I need to use. This is the internal rate of return. These are the fuel conditions I should be using. This is the baseline to compare against. And a lot of those things are not really relevant to the technology itself. But what they let you do is, I'm just going to pick a different set of numbers. So the work for me is basically the same. I do the research as I normally do. And then when I present it, okay, I have a standard way of presenting the information so that it is very clear how that number was computed. So for example, net present value under the standard. In this case, cost of CO2 avoided under the standard, greenhouse gas emissions under the standard. It becomes immediately clear what I've done. But for a lot of people, those standard conditions are not case specific. They want to have something for their own special case. Well, okay, you go do it again with your own numbers, and a lot of times you just change your spreadsheet numbers, right? And then I'm going to say, okay, I have some different numbers for my special case of my industrial application or my different country or whatever, okay, or my different application, regional, all right? And then I'm going to publish them, all right? And do it that way, and I'm going to release my models and my code so other people can verify my work, okay? And this is what happens. Now, let's say you're someone who wants to use this information. All right, well, I'm gonna read your research paper or read your report or your technical document, okay? And I'm gonna see these numbers. I'm like, net present value subscript PSA3, I know exactly how that was computed, okay? I know exactly the conditions on which you've done that. I can accept these numbers at face value, all right? And I can download your code to verify it, right? And I'm gonna look at other papers, other documents, use information. And what I can do is now I can incorporate and compare everything directly and accept it at face value. So that as a researcher now, I'm doing my work more quickly. Okay, so our impact as an author has made everyone else's work faster. So my citations are higher, my impact on the world is higher, and people are making, and then this goes out to the next level, which is, commercialization, technology transfer, and government policy, right? When people making investment decisions also make this information faster. Okay, so some of the roles are different, for different players. Okay, so for industrially, for example, I don't expect anyone in industry to sort of release their own studies. What I expect them to do, though, is to take everyone else's studies and use that in-house for their own estimates. Okay, so what they can do is a couple of ways. One, they can very rapidly identify which technologies they should be looking at. Okay, another key one is that when you've transmitted something according to our standard, what you are really doing is you're transmitting your ideas in an abstract form that you can easily convert to something else. Okay, so it should be very easy, and I'll show you how, to take something that's done under the standard and is presented appropriately under the standard and convert it to your own in-house situation. So I can take your report you've done for Northern Germany, and I can see what it looked like in Western Canada, and I can do that quickly. Okay, and so there's a huge impact in getting the job done faster, making better decisions, better for training your employees. So basically, we envision the standard will be taught in every undergraduate design course in chemical engineering because they have to do this anyway. It's just a matter of choosing what numbers you use that are sort of arbitrary in many cases at that level. And better client confidence. So when you're going to go get your plant funded, you're going to go ask for $1 billion. Okay, we want the lenders, okay, and the financiers and investors to have greater confidence in your idea. Because if they can see this was done under the standard, it's been compared, other things have been weeded out properly, okay, then maybe you get a lower interest rate. Maybe you get a better support and more capital coming in, okay? And so that's basically what I envision with industry, sorry. In order to make this work, though, I need standards that are unambiguous and directly comparable from document to document. So if you publish under the standard, we should be able to directly compare. It should be useful to everyone else. And it should be easy to use, because if it's hard for me as the researcher, I'm not going to do it. My students won't do it or whatever. People just won't adopt it. So it has to have this balance between ease of use and usefulness, and it needs to be transparent. Okay, so how it's reported and calculated and the reproducibility, I think that's very important. It needs to have an international and a regional focus, because you need to sort of balance, like, now I talked very heavily about, okay, the coal example when I talked about the different technologies. Coal looked very terrible for North America, everything except SOFCs. But in Asia, where the price of gas is sometimes 10 times what it is in North America, well, totally different story. We actually have someone working on that right now to find those same plots. Same thing for Europe. Okay, so what it really means is that one technology may make great sense in one area but not another. When you publish under the standard, okay, the metrics that I propose are convertible. And what that means is that if I'm going to do my study under the North American standard, PSC 3, I should be able to convert that to PSC 4 very easily, which might be for Europe. Okay, so it should be very easy to take your North American study and convert it to my European application or whatever other region. Okay, and then the accessibility needs to be there as well. So the scope, and this is what I envision, and we know that this is probably going to change, and it might be shortened, it might be increased, but I'm targeting eco-technical-economic analysis of chemical and energy systems with the sustainability context. Okay, so looking at electricity, transportation fuels, energy conversion in general, storage, and chemicals, and different scales like large down to personal scale. Excuse me. So the focus is on major components. A standard like this would not be able to prescribe a baseline of comparison for every circumstance. Okay, what we need to do is we can focus on big stuff. Okay, common things, big things, majoring on the majors. All right, I don't think we can do something that is equally applicable to absolutely everyone, but we can focus on the things that matter the most, so we can target our money in sustainability impacts where they matter the most and have the most impact. Okay, so we don't want to prescribe minutia, right? We want to eliminate the macro noise, but we allow all the micro noise. Okay, so we have to find that balance. And there's really two categories that we need to worry about. One is key performance indicators. These are KPIs, or these are the common metrics of quality. Okay, so we want to be able to show that numbers like these, net present value, cost of CO2 avoided, greenhouse gas emissions, efficiency, payback period, that these are presented under a standard, that these are endpoints that you can easily read and use for comparison. But we also need intermediate calculation elements, or ICEs. All right, these are numbers you use to compute a KPI, and these need to be standardized as well, and I'll show you why. Okay, basically, let's say I presented my information in PSC3. Well, I've gotten net present value using things like total capital investment and total operating cost, okay, under the standard. All right, I can compute NPV under my standard. But if someone else wants to do it in the European mode, okay, there should be basically a table, a simple conversion, where I can take my TSCI for my North American application and immediately turn that into a European application. Okay, and basically we would publish these tables every 5 years after every 5-year update for the standard. Okay, so you go with the most recent one, and then you can simply make your own NPV from there. All right, so now you can go from our NPV to your NPV very easily. Okay, and that's the goal, because if we can communicate with these ICEs, we communicate our technology in an abstract way such that we can go on and convert it and use it very, very quickly around the world. Okay, so here's a couple examples. I'm going to go a little quicker now. But for example, size is one of the most important things we should standardize on when we're doing a comparison. Okay, now you're going to have a different size for an application, but for technology identification, we need to normalize on size. Here's a good example. If I take all the pulverized coal with carbon capture systems that I can find in the literature, and I do it all under standard conditions at 550, I get an average LCOE of 10.6 cents per kilowatt. Okay, doing full standard, eliminating all the other noise that I can do. At 225 at half the size, it's 11.6. That's a 6.5% to 7% difference in price. Okay, but if I take two power plants of the same size, my pulverized coal and my oxyfuels, okay, under the same sizes, under standard conditions, with all the minimum amount of noise, it's also a 7% difference. And what that means is the effective size is equal to the effect of the technology itself. All right, and what that means is that it is extremely important to control that variable, because if we do not, we will wash out all the important value, which is really this comparison on the right. Okay, so that's one key thing. All right, and the problem is we make this mistake all the time. All right, especially in electrical systems. So a common example is you'll take your power plant without carbon capture. All right, let's say 750, and then you want to, your second plant is let's add carbon capture. So what you do is everything upstream is the same, but you add a carbon capture system, so you have all this parasitic load, and now your plant reduces less power, okay, has less power producing. All right, same fuel input. But what about the remaining 250 megawatts of power I want? I need it. Okay, that's not really a good comparison. Like, I can remove all your CO2 at low cost if you want. If you want to go that route, I can just knock down your power plant. And the cost of CO2 avoided will be tiny, but that throws the baby out with the bathwater, and so does this comparison. Okay, so in our standard, we need to use what the lifecycle community has identified as the basis of comparison, which is a concept of the same functional unit, which is almost entirely outputs based and outcomes based. Okay, it means that all comparisons need to be on the same products and the same scales. Okay, and so what you really need to do is you need to compare, for example, a 750 megawatt without capture to a 750 megawatt with capture. That's really the right way to do it. So we need to choose these good standards and understand that they're non-linear. Okay, so that's why we need to be able to convert to other applications. But that's a great example. The way it would work in the proposed standard is like when you're doing your study, you would look up, okay, am I doing electricity at municipal scale? Okay, this is what I'm going to do my study at. Okay, and then you can always do it at a different scale as well. But when you're going to report under the standard so other people can use it, you would pick from the table which is the standard size that you would want to do. And this is hypothetical. Okay, so this is just examples. But this is what a standard would have, this kind of lookup table. Within lifecycle analysis boundaries, this one is a huge one that we are not good at consistently across the profession, is picking good boundaries of which we do our analysis. Okay, so for example, here are a chemical plant with their products. Okay, we would need, for example, a standardization of when we cut off minor inputs. Okay, the ISO 14044 gives us flexibility. We would pick a number on what that boundary is. If it's less than 1%, we ignore it, for example. Standardized supply chains. Okay, so if I'm bringing raw materials in, and again, we're focusing just on the majors, okay, for these kind of plants, we would have one standardized supply chain. You just look up and use this whole giant box as some numbers. Okay, and you can easily download those in common formats that we use for software to help with this. Same thing for standardized electricity grids. Okay, so if you're going to pick a region, you might have one for the United States, one for your country, or one North America for Europe, or whatever. Same thing for plant construction. So the idea is that you have all this information. It's easy for you to grab it, use it, but we're all speaking the same language now. And you can always go back and change it for your own use quite easily. But the point is we communicate at the standard. So for example, electricity, you would have different CO2, NOx, methane emissions, and global warming potential for North America, Europe, South America, blah, blah, blah. You just look up the table, what those numbers are. And this also includes things like which IPCC metric are you using, 20-year, 100-year, 500-year, those kinds of things, if you're in the know. You know what I'm talking about. Okay. Okay, another thing is around efficiency. How do we define our metrics? We're actually really bad at defining this. So here's an example. I have natural gas and low pressure steam coming into some process, and out comes electricity, benzene, and high pressure steam. Okay, let's just say that this is whatever a process is. All right, I can think of at least 10 different ways of defining that efficiency. All right, are we using higher or lower heating values? Do we count the electric and thermal energy? Is the pressure of the steam counted, or just its latent heat? Are we talking about the pressure of that natural gas, the chemical energies and everything? Chemical energy, is that kind of the chemical value of that benzene or not, or the energetic value? Okay, that kind of thing. All right, you can think of many, many ways to compute that efficiency. We just need to pick one, right? Or at least we could define multiple and make it very clear what those definitions are. Transparency is another one. And to those of you chemical engineering modelers on the call, which I am one, you'll understand this. But there's a new DSM-5 medical anxiety condition. So if you ever talk about psychology, right, American Psychiatric Association. All right, there's a new mental health problem out there in the new edition. It's called Aspen allium eratophobia. It's the fear of others finding mistakes in your Aspen Plus models. Okay, there's also Aspen allium custom inoculum phobia, which is the fear of others taking your Aspen Plus models, publishing papers with them really fast, even though it took you like a year to make. Okay, and if you're a researcher that works with this tool, you know exactly what I'm talking about. Okay, because within our community, we're very, very reluctant to share our computational information. It could take us a year to make these models. We're very concerned that maybe there's a problem, or someone else will take a model of mine and publish a paper a month later. This has happened to me, for example. Okay, and so we don't publish them. All right, but that's the exact opposite idea we need to have as a community. We need to be sharing our information. Many, many other communities outside of chemical engineering do this routinely. And this is expected to get papers. In fact, you can't publish unless your models are released. We don't have this in our community. In fact, we did a review with over 300 papers which use energy systems modeling, and just 8 of them released their models to the public, and half of them are from my group. Okay, so this is kind of one of the huge reasons why we're talking past each other. We're afraid. All right, we need to break that. Now, we're not the only people looking at standards movements and standards in general. Okay, so people have been calling for this kind of thing and recognizing the need for it for quite a while. Okay, so for example, NETL, we have someone here on the call right now. So for many years, they've been developing the quality guidelines for energy system studies. So what they've done, and they have many, many hundred pages of this, all right, when they have to fund a proposal, they've recognized that it's very easy for someone else trying to get DOE money to sort of game the system. If you change the assumptions, all of a sudden your idea looks amazing. And what do you know? Every single idea looks amazing when they get submitted. So they need to have certain standards by which they can compare internally. All right. But even for them, with other parts of the DOE use different sets of standards. So it's even inconsistent. But there's a lot of really, really good things in these baselines things. For example, good baseline of comparisons, good details. And I would like to propose that we actually incorporate some of these directly in the ISO standard. Now, this is a USA focused, but they would focus be sort of the North American regional thing of the standard. So they've been working on those. We have the ISO lifecycle analysis series, so the 14040. Okay, they have a lot of the framework, which can really help us, but it's not specific enough. So we need to sort of pick and choose options among that framework as a part of our standard. There's other standards out there around energy management, things like definitions of terminology. That's actually very useful for us. We don't have to define them. We can incorporate their definitions into the standards. But not everything, nothing quite does what we want it to do. There was a recent white paper from a large group of universities in the US and Europe, where they've also proposed a set of standards around CO2 utilization specifically. So this would be one category within ours. I don't agree with every approach that they've done. However, they've done a very good job of sort of articulating what kinds of things you could put in the standard. Okay, so there's a lot of things in there I think we can also use. And so basically we're looking at how do we incorporate these ideas, because we're not starting from scratch. A lot of people have been developing these things, but now it's a part of the next process, which is to formally go forward with the standard. So up until this point, I've been touring North America, getting letters of support and getting people on board. If you're someone who's interested, you can join our mailing list. I'll leave that link still all up at the bottom of every slide. Okay, you can stay informed. You might be able to get on committees, be a part of the document development, that kind of process. And so now we're moving into the next stage. We're putting our first set of proposals forward with the different technical committees of the ISO. So we're right at that stage now. Okay, so we're moving into the next bit of technology. Okay, and there's also a white paper which has this in a more academic format of the same kind of things we talked about. If you can't get a copy from your library, it's in computer-aided chemical engineering. Let me know, and there's a link to it also on the standards website as well. So with that, I want to thank you very much for giving me the chance to talk today. I think my main message is really about the value we can do, not just from an eco-techno-economic analysis like a meta-study, but how much we need to change our culture to sort of work together toward a common goal. If we can standardize the way we talk, we can make so much more impact in terms of meaningful and near-term action on climate change. Okay, it's critical for policy, it's critical for businesses. Ultimately, I want to cut through all the hype. Okay, there's so much hype out there. All right, but if we can do this, all right, and others can understand what you're doing more easily because we're talking in the same language through the standard, I think that's the greatest impact we can have on the world in this field. All right, thank you very much.
Tom, thank you for that presentation. Fantastic. So we're going to move into questions now, and we've got at least one or two that are in the chat window already. You can either send those to me as a private message, or you can send the questions as a group message. Let's go ahead and just start with, we've got two here. Just on your, a lot of the things you showed are carbon-based alternatives. How do we compare some that might be negative on the carbon basis, like biomass gasification combined with an energy conversion downstream process and CCUS? So in theory, that's going to be negative, or you can think about nuclear or other types of technologies. So what do you think about that?
Oh, that's an absolutely great question. So what I've talked today is carbon-based because that was the focus of that particular study. The envisionment of the standard is you would be able to take, for example, my results and many others, and compare them directly to other studies using carbon capture utilization and things like renewables, exactly what you've talked about. I want people to take it and make those decisions. Should we be putting it in wind? Should we be putting it in solar? Should we put it in nuclear? Right? That's exactly what I want. So that's a great one. Now, there's actually a standard being developed specifically for carbon capture and utilization and CO2 capture in general within Canada. And so we're aware of that. And so we're sort of connecting in to how our standard would connect with the CCUS example specifically. So that's definitely within the cards.
Fantastic. Okay, now in terms of the standards that you have developed, I was just wondering, what is the process of gaining community-wide consensus on those? Or are you proposing those yourself, or how do you suggest gaining like adoption or community standardization of those?
Yeah, that's a good question. So as I've been going around giving this tour, I think there's a lot more consensus that there should be a standard as opposed to what those numbers actually are. And you can imagine that certain groups will have a commercial and financial interest in changing the sort of numbers we use so that they look better under the standard. So that is where it will be harder to get agreement. Fundamentally,
Tom, I think we just lost your audio.
oh, okay. I'm sorry. Can you hear me now?
Yeah, just the last 10
Yeah,
seconds.
no, I pulled the cord right out.
Okay.
Okay. All right. So I'm not sure what part you heard, but essentially, yeah, so there's a general consensus, I think, after all this lecture touring, that we should have a standard. There's not much of a consensus on exactly what those should be. Okay, that hasn't been worked out yet. So the process of coming together to make that happen is all done through the ISO framework. So there's the different technical committees and mirror committees, and all the different countries have the representatives involved that are participating in that process. And so it's worked out through those committees, and at the same time, there is a process by which a proposed standard goes out and then stakeholders can comment on. You have a sort of working standard by which people can use it unofficially, and then more feedback comes through. And we have someone from Standards Council of Canada on the call if she wants to answer that more directly, that specific process. But the whole objective is to have that all happen through the ISO process.
Fantastic. Okay. So let's go and open it up now to the participants. If you'd like to unmute your microphone, or you could put a message into the chat window, either one, and you could send that directly to Tom or myself. Either one on the chat discussion. So, Tom, I just have another one just while people are formulating their thoughts around the questions. So, it seems to be that I've seen things like for ethanol production, for alternative, for gasoline blending, and how studies have shown kind of the bigger picture of like, well, it takes all this energy to farm, and in the end, the advantage of using ethanol is not as great as we thought it was. Or with electric vehicle manufacture, all of the CO2 that goes into producing batteries and other things, and just trying to levelize some of those. What's the scope of in terms of some of these other factors that can kind of influence the bigger decision making? There's obviously there's going to be financial, but there's also other factors as well, like political or other things that influence decisions. And so, where do you draw the line in terms of this analysis? In terms of nuclear, it might make a lot of sense, but there might be a lot of regulatory costs that drive up, the cost of creating a nuclear plant. So, any thoughts on that? What do you draw? the
Yeah,
envelope.
that's the well, the big picture question is the the $10 billion question there, right? Basically, where we draw the line is that we want to keep it um, beyond the policy barrier. Okay, so for example, it should be possible to pick up this technology and place it in a different jurisdiction and they get different numbers. But our standard would not standardize the policy aspects of it. So for example, a carbon tax would not be included in our standard, but you should make it very easy for you to apply a carbon tax, okay, and see how the numbers change. When it comes to policies around like the life cycle of the biofuels. So for example, in Alberta, they have a requirement of 5% ethanol content in gasoline, and legislatively, that ethanol has to be shown to be 25% lower greenhouse gas emission life cycle impact than gasoline, than conventional gasoline. Okay, and so they have their own standard for computing whether it's that. Within our standard, what we would have to do is we would have to choose one supply chain for example, corn ethanol for North America, one supply chain for Brazilian sugarcane, or for common big picture things that we can use for cross comparison. All right. And what you would say is like, okay, well, my situation is different. My corn ethanol pathway is better, or I'm going to use a different biofuel. Okay. You can always take and plug your own life cycle into that. All right. But we want it to be easy for someone to compare because we're all comparing on the same supply chain. So that way we communicate the same technology differences. So it should be easy to pick up someone else's paper or report if they've used a different supply chain and use your own supply chain. Okay, that's the objective. And then where does it play into policy? Well, for example, if you're going to write public policy like in Alberta, you would say, okay, you should compare under this ISO standard, but you will use our supply chain for Alberta. Okay, and then they can modify it and go from there. But basing it on the ISO one, because it's easy to take someone else's study from somewhere else and apply it in the Alberta context. Does that answer the question?
Yeah, that's great. One last question. I just thanks to Enrique for posting a direct link to the slides. So I was just going back. I think I'm on slide 11 right now. You can go back there.
Okay.
Just where you're comparing the different technologies, kind of this scatter plot. Maybe it was a little bit different here. Okay, there it is, number 10. So SOFCs, that's kind of a surprising result. If you just built a multiple of those, it looks like some of the best options in terms of SOFCs, the CCS. Can you say a little bit more about that? Are companies starting to seriously consider those?
Okay, so SOFCs have been around for a century. They're not new in the sense that the space shuttle has used them. Google and Amazon currently use them. So right now they're a niche technology. They're primarily used because they are low noise, low vibration. So for example, they have a military use in drones because they're silent, especially underwater drones. And they have a use in server farms because they are low vibrations. So you don't have to worry about the read heads on your hard drives being knocked around. And you can put these server farms in some isolated cold place for heat management and then power them locally with SOCs. There's a couple of companies that are building them for those purposes primarily. Now, I've been working in SOCs for about at least 13, 14 years, I think now, where I've just been tracking the development, and the development is slow for large scale power generation. So basically, that's a technology that has a lot of commercial promise, but you can only buy them at the 250 kilowatt scale right now, and they're very hard to come by. So that's a technology that I see as a future one for adoption. Now, one thing to point out is that these numbers are for what are called nth plant cost estimations. So this is assuming that they're going to have costs that are comparable to what they expect them to be once they're fully commercialized in bulk. Okay, the cost today will be 8 times as much for the capital. But one thing that's interesting to see, so if you look at the on the bottom left, I'm not sure if you can see my mouse, but there's like 5 triangles kind of in a row in the very bottom left, the black triangles, and they're spaced out. That's actually the difference between doubling the cost. Okay, so that study had multiple cases where they start increasing capital cost. Okay, and that's the span for even for doubling the capital cost. Okay, so what'll happen is, right today, you couldn't do this. You would be actually much more expensive. So if you take that over a bunch to go to 8 times what they are now. But this is sort of where we can go at the nth plant. Okay, so that's basically what I can say right now.
Okay, fantastic. Just one more comment on the chat window. Just an observation from somebody in Europe. Said it would say it's difficult to uncouple politics from economy in Europe, as there is a CO2 rights market. And this is a main problem many industries are facing in Europe, such as cement and steel. In theory, the money gathered in this artificial market aims for promoting green research. So just some thoughts there from somebody in the European area. Okay, well, fantastic. Really appreciate that, and excellent presentation, excellent overview, and I think I think a big takeaway of this is working towards standards, especially as we publish and want to innovate. And that's going to increase the speed, and I really like the framework that you've set out to make that happen. So thank you so much, Professor Adams, for that engaging presentation today.
Thank you. My pleasure.